Welcome to the course on power quality. Today we will be discussing power quality improvement in distributed generation sources based microgrid. The outline of presentation is introduction to microgrid, then power quality improvement in grid integrated solar PV based microgrid, power quality improvement in grid integrated wind solar PV based PV battery based microgrid, then power quality improvement in grid connected small hydro solar PV and battery based microgrid, and power quality improvement in grid connected wind solar battery and DG set based microgrid, and power quality improvement in microgrid for electric vehicle charging station. So, this is typically the concept of microgrid. Microgrids are electrically distributed system containing loads, distributed energy sources such as distributed generator, storage device and controllable loads that can be operated in a controlled coordinated way either while connecting to the main power network or while islanded. And traditional grid that you have a typically the generation on remote places, and then you have a transmission line and distribution and consumption. So, one way is a electricity move only one way, but in case of microgrid you have a local generation, bidirectional power flow is there of this typically in the microgrid along with the information, because in today we have a lot of information protocol, to that also information flows, so that the network can be properly controlled in microgrid like. And how does microgrid work? The traditional grid connect homes, business and other buildings to central power sources, and when part of the grid needs to be repaired, everyone is affected, and microgrid generally operate while connected to the grid, but importantly it can break off and operate its own using the local energy generation in times of crisis like a storm, a power outage or for other regions. And microgrid fueled by distributed generators, batteries and renewable energy sources, and benefits from the microgrid for the utility, better power control and reliability, reduced energy losses, dynamic demand response, realistic pricing model and increased demand response capability. And for customer it provides choices for different services and reduced prices and improved reliability. And for society it is an integration of green energy sources like solar, wind, biomass, geothermal. And applications of microgrids are microgrid candidates comes like institutional campus, side hospitals, university, commercial industrial facility, then remote off grid communities, military bases, data centers, municipalities. And microgrid can vary in size from 3 kilowatt to megawatt like a generation resources type, storage and advanced control. And the investment can be significantly and return on take in years, and these are the typical examples of microgrid, which normally you have a local generation with the renewable energy sources. So, the microgrid project in India, there are 63 solar microgrids installed in India so far. India now has world largest solar array at Kamathi, Tamil Nadu. At the middle of 2018, India scaled up renewable energy goals from 175 gigawatt to 277 gigawatt over the next 4 years, with about 40 gigawatt of the goal representing rooftop solar. And these are typical photo of world's largest solar PV at Kamathi, Tamil Nadu. So, one of the most important energy access program in India is 24/7 power for all, and intensive effort is improved to energy access to the individual household through home solar kit. And the amount of 4.4 billion Saubhagya Pradhan Mantri Sahaj Bijli Har Ghar Yojana on solar lighting program launched in 2008, delivering low cost and free home solar kits to many rural households, like typical example here electricity distribution line in Indian village. And India also has a village electrification program called DDUGY, Deen Dayal Upadhyay Gram Jyoti Yojana, which was launched in 2014 and drive improvements to the electric grid in rural areas. And Chhattisgarh Renewable Energy Development Agency (CREDA) has installed and operated more than 500 solar microgrid, and Husk Power has built over the 75 microgrid in India and Africa, connecting 15,000 homes and business. And these are typically solar lighting just at the beginning. And India first industrial solar microgrid commission in Gujarat, that is Swiss multinational giant ABB today announced its commissioned India first industrial solar microgrid at Vadodara manufacturing facility in Gujarat. And of course, coming to the problem of in AC microgrid, the synchronization of distributed generators like ingress current, problems like transformers, induction motor, induction generators, and 3 phase unbalance like single phase loads, single phase PV generation. And recent trends are introduction of many DC loads like AC DC and DC AC conversion are included. Introduction of diesel distributed generator with the DC output like a photovoltaic, fuel cell, wind turbine, micro turbine, gas turbine, and needs for higher quality of power, and DC coupled micro turbine DC, and then DC microgrid with nano grids and DC distributed power system like DPS, and synchronization and desynchronization with the utility grid like. Now, coming to the power quality improvement in grid integrated solar PV based microgrid. With the typical system like which have a single stage PV based microgrid. So, we have a solar PV array with the single stage, and we have a here with the buck boost converter of the battery. This buck boost converter of the battery like allow to have a maximum power tracking by controlling the DC link voltage. So that you can eliminate the one converter, and it allow the battery voltage to be at optimum voltage. Apart from that, now normally the under load unbalanced condition second harmonics there in the DC link, that can be also it does not flow into the battery, can be curtailed. And then this total system you can say can be synchronized to the grid when grid is available and provide the interruptible power to the local load, maybe linear or non-linear load, and you have a synchronization and islanding both. So, if grid comes, then you have to synchronize to it, so that you can exchange the power from the grid depending upon the cost of the, you can sell the costly power at the, when the electricity is costly on the grid, you can sell to the grid, and when there is a cheap power, then you can store the power in the typically into the battery. So, you can call it like you can take a benefit, all benefit of battery energy storage system, and you can avoid the intermittency of the solar generation as well as intermittency of the load also. I mean, as far as load is concerned, even intermittency of the grid also can be taken care. So, this is something like you can call it a solar based microgrid. The control history follows has the following parts. Then maximum power tracking algorithms have to be used for maximum power extraction from solar PV array, and control of voltage source converter for current control in a voltage source converter when you are having a typically in grid connected mode, and synchronized controller when you have a typically grid appears, a grid disappears. So, you have an islanding and you have to connect back. So, you have to check the phase angle of the point of common coupling voltage as well as the grid voltage, and you have to control for the synchronization, and then voltage control you of course have for islanding operation of voltage source converter, and battery with the bidirectional control. This is the typical I mean when you have a grid connected, we use the current control when you have grid connected mode. So, we are sensing the load and we are extracting the fundamental component of the load, and so that on the grid side we are, and we calculate from the sense line voltage the phase voltage, and we calculate the template. So, this is the typically the load component. Then we have a the maximum power, I mean typically the feed forward term, and then we have a even the battery component, we want to exchange the power with the battery, and this give us the typically amplitude of the grid current. Then we have a template. So, we have a reference grid current, and we have a sense grid current. So, we control this converter in grid connected mode like the. So, here we have a estimation of unit template, and then terminal voltage, estimation of active power component, generation of reference 3 phase current, generation of gating signal. So, this is virtually what we have. Typically the line voltage we are sensing and calculating the phase voltage, and from phase voltage we are calculating the amplitude, and then the template we are calculating from that. And then we are extracting typically the fundamental component from the typically from the load current. If load may be you can call it the may be unbalanced, or it may be like a having a polluted load current. So, that takes care of your typically calculating the fundamental component of your load current from A, B, C all 3 phases, and finally, we get the fundamental component for all 3 phases, and of course, they may be unequal under unbalanced load. Then you have to take average of this, so that load balancing is relies on that, and then you have a feed forward term for solar power and feed forward term for battery. Then we get the amplitude of the supply current from the load current minus the PV power minus the battery power, I mean like, and that give the power flowing into the grid like, and then multiplying the template. So, we get a reference grid current, and with the comparing with the sense grid current, we are able to have a current control of voltage source converter with the improved power quality on the grid side with this current controller like. So, these current are given to hysteresis controller for producing switching pulses for voltage source converter. These typically like when you have a operating in voltage controller mode in islanding mode. So, we sense the typical, we have a reference voltage, we have a sense voltage, and we have a discrete proportional resonant controller which have a steady state array 0 that give a reference load current, and we have feedback load current which give the gating signal for voltage control for islanding mode. And then once you have a grid appearing, then you have a typically you have to calculate the angle for both, and with the PI controller you make the these 2 angle closure, so that error is minimized to 0, and that give you the small, you can call it frequency change. We have a reference frequency, we get the net frequencies, and that give the angle after integration. So, this virtually causes the, you can call it the point of common coupling or the your voltage source converter voltage output after the filtering towards the grid voltage, and that synchronizes. So, this is in islanding mode voltage control mode. So, we have 3 phase reference voltage, we have a error voltage, and that we pass on to virtually to calculate the reference load current from this error for all 3 phases, and then we have a typically the current controller calculating. And for bidirectional current control, we have a DC link voltage, we have a sense DC link voltage, we pass on through low pass filter. So, that only DC component is there. We use the PI controller that gives the battery reference current, we have a sense battery current, and then with battery current again we pass on to PI controller. The output with that we compare with the PWM signal to generate the gating signal for the 2 devices of the your bidirectional buck boost converter like. So, bidirectional control consists of 2 main parts, voltage control of DC link voltage and current control of the battery, and VDC and VDC are compared to get the error, and from this we get the reference battery current from this PI controller, and then we have a battery current error, and again we put the PI controller that give the virtually duty cycle for typically for the control of the converter of the battery like. These are the typical data of the system, which system is considered for, and these are the simulated data. So, when the grid was there, you are feeding typically the load with the exchanging the power with the grid, but when the grid disappear, the load is not affected because load voltage still remain, but certainly the converter voltage changes because that was exchanging the power, as well as battery current also changes. So, battery now typically you can call it might be discharging more to feed the load. And similarly, when grid appears, here grid was not there, but load and load voltage are not affected, but when grid appears after few cycles, you have to move the synchronization process, and then you close the switch typically at this point, that is this, and then the grid current start appearing, and you go to current control mode. So, here you are operating virtually voltage control mode, and then you are going to current control mode. This is typically the performance when your load is changed, on one phase load is removed to unbalanced load, and how the system responds to it is not affecting the voltage and current correspondingly, and here it is when solar insolation is changed. So, accordingly the grid currents are changed also. And these are typically the power quality performance of grid current with the TAD 4.21%, where the TAD of your you can call it of on the load is 20. So, it is able to provide the working like a power quality improvement on the grid current, even supplying the non-linear load like. So, coming to hardware implementation, this is the data for hardware implementation. Processor is used typically Opal RT as a processor here for implementing the control algorithm with a current sensor and voltage sensor in the practical system, and these are the data of practical system. These are typically photograph of the practical system, and this is you can just clearly see here. Here the typically the grid is disconnected. So, we are operating in current control mode, typically grid voltage, grid current, and coming here, and this is the load current. But if grid is also disappear, still load voltage is there and load current is there, that is not disturbed like, and this is of course angle goes out of but when the grid comes here, load is not, load voltage and load current are not affected, but when grid comes it goes towards synchronization, and here we close the switch and grid current start appearing, and then you can clearly see how it is typically the change of connection of the grid and grid current appears, and how the angle is get synchronized like. So, here it is the dynamics correspond to that your removal of one phase of the load, how the all the internal signal are changing, but the grid current remain balanced and sinusoidal, reference grid current as well as your actual grid current remains sinusoidal and balanced like. And then the typically you can say change in the solar insolation level. If solar insolation changing, accordingly you can see clearly the how the grid current is typically is not changing, it is not affecting because battery takes care of the intermittency of the solar here in both the cases, or even there is no solar generation, still we are able to feed the load without any disturbing like. And this is the maximum power tracking typically of the 4600 watt per meter square and 1000 watt per meter square of solar, and they typically the response in the change of the load. If you increase the load, how the typically the grid current is affected and your converter current is affected, and how the your typically the your load power is affected like. And this is the TAD you are getting typically of order of 3.5% of the grid current, where the TAD of the voltage was 2.2% like also. And here you are getting in island mode the TAD of voltage 3%, where the here the current TAD you are feeding highly non-linear load or order of 28% in islanding mode also, or voltage control mode. So, at the instance of grid outage, the microgrid feeds the load and the microgrid transfers from current control to voltage control mode. After restoration of the main grid, the microgrid synchronization to the main grid and the mode shift from voltage control mode to current control mode, and system operates trouble free in grid tied and standalone mode, and the battery connected through bidirectional converter has maintained voltage for MPPT to appropriate voltage across the DC link, and the system has demonstrated the dynamic performance and steady state behavior under solar insolation change and load variation, and the grid current TAD and voltage TAD has been observed less than 5% as specified in IEEE 519 standard. Now, coming to power quality improvement in the wind solar PV with battery based microgrid. So, this is the system where we have a like a wind generation from synchronous generator, and we use the variable speed generation because we are able to get maximum power tracking we can use, and solar also we use the maximum power tracking, and here on the DC link we are keeping a battery with the buck boost converter. So, this is the converter for the machine side converter, this is the grid side converter, and this we are feeding to the typically power to the grid like also. So, typically here the control of grid side voltage source control, control of machine side converter, control of bidirectional converter, and extraction of maximum power from the wind, extraction of maximum power from the solar. So, this is the algorithm of course using adaptive you can call it maximum power tracking algorithm per turbine observed for solar, and that is the way how we are doing for the typically with the PI controller, and these are we are extracting the load for load compensation the fundamental component as we have been done earlier, and averaging then taking LPF, and this is the feed forward term of the wind, feed forward term of solar, and the loss for voltage source converter. So, that give us net weight or net amplitude of the current, and we multiply it with the template. So, we get the reference grid current, and with the sense grid current we are able to give the gating signal to the switches like. And this is the typical case like for you can call it the machine side converter. So, we have a wind estimated speed, you can call it wind speed, generator speed and wind power from MPPT that give the reference wind generator speed, and we have a estimated speed. So, we have a speed controller, we get the torque producing component from vector control, and we have a then direct axis current typically to maintain unity power factor with power excitation and then zero sequence. And from this of course, we are getting from typically from these estimation we are getting the theta for transformation for DQ to inverse power transformation, we are getting reference current, we have a sense current of the generator wind generator, and we get the gating signal for the wind machine side converter, that is wind generator like. And this is typically what we are doing like typically for constant voltage regulation, if it is typically or we are talking about the with the battery depending upon the SOC, and then use the PI controller for battery current control for bidirectional converter. These of course, the typically the modes of MPPT of the wind maximum power tracking algorithm, and this is for solar maximum power tracking algorithm like. Then this is of course, the algorithm corresponding to wind power maximum power tracking to get the wind reference speed on the power, and then this is the solar MPPT equation for getting typically the reference MPPT voltage of the solar. So, that we can, and these are of course, calculating the phase voltage from the grid voltage, the line voltage, and then the amplitude of the voltage, then the DC link voltage error, then the feed forward term of the wind, feed forward of the solar, and typically the weight corresponding to calculation of the weight of the load current. From this we are getting from the this error from the load current and with the reference load current, and then we are able to get the typically the load balancing, we are able to take averaging of the all three phase weight corresponding to the load current, and we are getting this load current amplitude for active power, and net weight we are getting for corresponding to load current. Then the loss it comes from the grid minus the PV that is fed to, and then the wind that power fed to the wind. So, we get the net weight, and multiplying the template we are able to get reference grid current, and then we are able to use the grid current controller. This is for typically for the wind, you can call it the wind, this you can call it the machine side voltage source converter control. So, we have a wind speed error for maximum power tracking. So, we are using for a speed controller that give us the quadrature axis component of current, torque producing component of current, and then direct axis we get from typically for unity power factor operation IDQ, and these we can transform to, as I already explained in the block, we get the power transformation to inverse power transformation to get 3-phase reference current for the generator, synchronous generator, and we have a sense generator current to have a current control. These are typically the experimental waveform after running the system. So, these are synchronous generator current typically, here for different speed, wind speed. I mean here 7.2 meter and 12 meter. I mean, and this is typically you can call it like a wind velocity, then wind generator speed, then one winding current, and the angle for estimated angle. So, speed estimated angle and estimated wind generator speed like, and these are typically you can see the typically the grid current, load current and converter current, and typically the actual your generator current typically, and non-linear load and converter is working as a active filter, and you have a TAD of the voltage 1.9% and non-linear load current TAD is typically of 17.9%. These are typically dynamics that when wind speed increases or wind speed decreases, how the typically it is going to be change the say direct axis quadrature axis current, and then how the internal signal for the algorithm is changing here typically on the grid side for the different dynamics of the wind generation, and how typically it is a solar reduction, solar power generation reduction and solar power increase, how these signals are generated like virtually. And then here you can clearly see when load is removed, the grid current increases on the grid side, and typically load, and when there is a change of the load, so on two phase loads are changed like, so dynamics of the load you can call it, but still power quality remain improved. These are corresponding to the signal, internal signal of the algorithm corresponding to the load change to get the net weight corresponding, that is the net weight what we are getting from the algorithm like corresponding to, and these are typically the you can get power flow into the battery typically charging here it stops at the power generation less, and then battery charging take place. So, that power flow into the battery during the dynamics corresponding to the load change also, and then you can clearly see here that the grid current TAD 2.3% when the voltage TAD even 2.2% or so, and this is here again corresponding to the different power generation here 2.69, here you are having a power exchange only 1.43 kilowatt like, and then the typically you are taking the power from the grid, I mean different power from the grid, how the performance is there, but you can in all cases you can see the TAD of the grid current remain less than 5% also. So, now coming to the another topology of microgrid based on wind driven synchronous generator, typically synchronous reluctance generator and solar PV, and then we have a typically the battery here connected on the DC link, and we have grid side converter connected to this with the synchronization here, and having a linear non-linear load feeding the local load also. The typical control architecture or control algorithm for this is typically for current control mode, this is for voltage control mode, and here we have a certainly filtering the voltage for typically calculating the template and typically the pulse generation here, and of course, we are using the filtering for the voltage as well as current for this algorithm. And these are the typical after implementation the results like you are feeding a non-linear load, but the grid current remains sinusoidal, and the load where the load TAD is 27%, here the current grid current TAD only 2.4% like all. And you can clearly see even very distorted grid voltage also is capable of, I mean this is the algorithm how we are filtering, okay, using the filtered signal here even from distorted voltage positive sequence voltage we are extracting for the purpose of the control, and then we are extracting the current also out of it, and these are of course for algorithm when the solar PV generation increasing or typically the load you have a load perturbation by making the load unbalanced. So, how the response of the system is taking place in for improving the power quality on the grid side like, and then it is typically kind of like a islanding, I mean like the grid current is reduced to 0 when your grid disappears, but still load current is not affected, like, and when then you have a grid appearing and how we synchronize to the grid, so resynchronization of the grid too. So, now coming to the power quality improvement in grid integrated small hydro solar PV microgrid. So, we have here a small hydro connected to the system, we have a solar, we have a battery here, and then we have a synchronization islanding to the grid like. So, this system using the solar and small hydro that practically can happen on the canal. You can have a solar panel as well as you can have a small hydro run over river kind of plant. So, you can exchange, of course, you have a battery storage, you can exchange to the grid when grid is there. If grid is not there, you can feed to the local load, and such system are coming up now can be used easily for charging infrastructure of the vehicle very close to the canal, running canal also. So, control here we have to take maximum power taking from solar PV generation, and then voltage we control the voltage source control algorithm in current control when grid connected mode, and voltage control and frequency control when islanding mode, and then we have a switching algorithm for synchronization and islanding like, and then bidirectional current control. So, this is typically in current control mode when grid it is connected to the grid, we are extracting fundamental current for the 3 load current, And we have here the feed forward term for the solar, then feed forward for typically for small hydro, and then power, whatever power we want to exchange from the battery, that also we are taking. So, that give us net here typically the weight, and you have the load, typically all three load current, and that we really get from here and divide by averaging for all three phases. And we have a typically amplitude of the grid current, we have a phase here, and then we have a reference grid current, and we compare with the sense grid current and give the gating signal. So, this operates, you can exchange the power to the grid at improve power quality, the power quality of the grid is improved. And this is in the case like islanding mode, that you are operating the system in islanding mode, and it is a synchronization and it is operation in islanding mode, voltage control mode. We are controlling the voltage here also, and typically this is virtually how we are calculating the template for this purpose. And this is how the control, the synchronizing controller checks that grid is, grid voltage, grid frequency as well as grid angle are within the range, then only the synchronization process take place like. And then the typically DC link voltage control with the battery control, which we already discussed earlier. And then of course, the template calculation and amplitude calculation of the from phase voltage of the grid, and then the feed forward term for the small hydro, feed forward from for solar, calculating from here, and then we have a feed forward for battery power also. So, we get the net, typically here we are getting the net amplitude of the grid current, and we are getting 3 phase reference grid current by multiplying the template with the typically with the amplitude of grid current, and we have a current controller for that. And these are the template for the typically for the hydro, and you can call it like a, we are having a amplitude of the voltage, then we are getting the template, quadrature template for, and then the error typically we are getting for frequency control, and this is the frequency control output we are using for, and that we are considering typically error in the voltage for the computer. So, we are able to get the voltage PI controller to regulate the voltage, and that we are getting the typically the small hydro current from typically all 3 phase load balancing, and then typically from the for the hydro, and if amplitude of reactive current comes certainly corresponding to the voltage regulation. This is typically the reference current for, you can call it the hydro, the active component and reactive component corresponding to the hydro for generation, and then the typically for synchronization the error between the angle calculation, and then finally we get the frequency, which are some of the typically the frequency plus the PI controller output like. And these are typical results, like you can see here, here is not a grid and load is fed, but here once grid appears, then we go on synchronizing, and we typically close the switch here after few cycles once it attains the angle completely close to the, and the grid current is start appearing. So, that is the synchronizing process. You can typically see here also in gist like how synchronized, but load current are not affected, load voltage also not affected, and grid current remains sinusoidal and balanced like typically here like, and how the dynamics is changing during the island to grid transition mode, and then the island grid connected mode to islanding mode, but load is not affected because load voltage is also not affected as well as the load currents are not affected like. So, dynamic correspond to different modes, and the harmonic spectrum in case of synchronized mode and in terms of islanding mode. So, islanding mode, even you are feeding a very highly non-linear load current, but your TAD volt of the voltage remain quite low, even you are feeding a very highly non-linear load, but when you are connecting in the grid, that your grid current TAD is quite low. Now, coming to the another case study of power quality improvement in the grid connected wind, solar, PV, battery based DG set based microgrid. This is the system made quite reliable. So, we have a grid, we have a DG set, okay, so that we can reduce the size of the battery. We have a battery, we have a wind generation, and we have a solar generation. So, to make the reliability, we are using DG set. So, either you can synchronize to the grid or you can synchronize to the DG set. If the battery, you can don't have enough energy from solar generation, wind generation as well as battery drain out like. So, here in the control we have MPPT for typically for the your solar, and control of standalone mode, control of grid connected mode, transition from standalone to grid, and from transition grid to standalone mode of operation. This is the maximum power tracking of the solar generation. We are getting a reference PV voltage from this, and this is typically the voltage and current control for grid connected system. So, we are typically, you can call it like a reference voltage, we have a load current. So, it is a virtually you can call it the current and voltage control like typically, and the current controller for voltage source converter operating with the inverter, either grid connected or you can call it, it might be operating the DG set mode. There are both the modes are similarly operated in the manner, and this is the how we are extracting the fundamental component from the distorted voltage. If you are typically for an angle calculation for typically for synchronization, like how synchronization take place. We get new frequency and then the angle for synchronization. So, we have a for in voltage control mode, we have a 3-phase reference load voltage, we have a load current, we calculate in dq, and then we calculate typically the, you can call it reference active component current, load current minus wind power generation minus the PV power generation, that is virtually flows to the grid, and then we have feed forward from the wind, feed forward from PV, those are, and we get the reference grid current from transformation to dq2 with the grid angle. So, and by sensing the grid current, we have a current control on the grid current with the power quality improvement, and this is how we really calculating the angle. And this is the typical case of, you can call it here the islanding operation of mode, but you have a sinusoidal voltage, even the load current are non-sinusoidal. Now, you are getting the angle, and there is a perturbation, you can call it in solar power generation. The system is still on feeding, and battery takes care of the variation of the your, like you can see the battery power, battery go on discharging when your solar power generation is less. And here is the synchronization, you have a islanding mode, and where grid appears after few cycles of synchronization of the angle. Once it is synchronized, you close the switch and you connect to the grid. So, grid current start appearing like, and similarly when grid disappears, so still load voltage and load currents are not affected and it remain on operating. These are typical experimental results, like in islanding mode, you have a voltage TAD of 2.7% even at non-linear load when you are feeding the highly non-linear load of this nature, like with quite high TAD. And low TAD here you can call it like a typically, it is a grid connected mode. So, you have a grid current TAD of around quite low 4%, and this is typically when you are operating with the DG set operating mode. So, you are able to have a DG set current, load current, and then compensator current, which are providing active filtering or compensation or improving the power quality on the DG set, like in this operating mode and feeding the non-linear load. And these are the typical dynamics where the grid appearing. When you can see load voltage and load current are not affected. When grid appears, after few cycle of synchronization, grid current start appearing once you close the switch, and this is typically desynchronization where grid disappear, but load voltage and load current are not affected. And once it is synchronization, how the angle take place along with the current, like and voltage, like. So, these are the corresponding dynamics when solar generation changes and wind generation changes, like, and the performance with the DG set, like typically how it is the typically goes to the DG set operation, the load change and your generator grid disappear, and you have a generator off also, then you synchronize to the grid. So, generator you operate with the minimum time, like, and this is the typically another configuration where we are using the for wind generation squirrel cage generator with the variable speed, and we have a solar generation with the battery here, we have a load, we have a of course the you can call it DG set with squirrel cage generator, and we have a 3-phase grid. So, either you can synchronize to the DG set or to the grid, or you can operate in islanding mode if you have enough energy from solar and wind along with the battery to feed the local load. But you can exchange once grid is there, you can exchange the power with the grid, but if you have a deficit, you can take grid is not there, you can take from DG set, like. So, it has the control stage categorized into 3 different parts, like load side converter control for standalone and synchronization control, load load side converter control for the grid connected mode, and machine side converter for and solar PV control. So, this is complete algorithm for grid connected mode. This is the portion, this is standalone mode, and with the synchronization take place, and this is standalone mode of operation of this system, like. So, the machine side voltage source control through indirect vector control, field oriented control, and because you have to operate in wind power generation for variable speed to get the maximum energy out of it, and we use the indirect vector control in DQ frame. These are typically the expression for your D axis current and quadrature axis current with the speed controller equation, and then you get the typically 3-phase generator reference current for generation, and then you are able to have typically here the for the reference current wind and feedback current, and you have getting signal for voltage source converter or machine side converter for typically for maximum power tracking, like. Then you have angle calculation corresponding to rotor reference frame, like. These are the typical results when you are typically the wind speed is changing, how it is the typically your you can call it grid voltage, grid current. So, grid current will reduce when wind generation is less, but load is not affected also, and this is the case when typically the dynamics response take place forward under the solar intense change. So, solar generation is changed, that is the reason the grid current is also typically reduced, and you have a typically load current and load voltage are not affected. And similar case for your load unbalance. So, when load is removed, one phase load is removed, but grid current of course increases slightly, but it still remain balanced and central at unity power factor. The compensator takes care for compensation of this. These are typically the hardware of the prototype developed for the system. So, you can say grid current and grid voltage, where the load current and grid voltage are shown here, and typically case of it remains, and you have a quite good TAD typically of remains of the current less than typically even 5%, and voltage TAD also less than 5% you are observed even in the distorted grid conditions like also. And when you are having a load reduction, how the your battery current is changed and solar generation is changing, how the system typically PV changing and battery is getting charged more like. Similarly, when you have a typically the load change, load balancing take place, but how the system response is taking care during this operation of the grid side current like, and how the with the solar generation also if it is changed, how it is really affecting the performance on the battery current as well as your load is not affected in all the cases. And here you have a typically islanding mode and synchronization mode back to the grid like here, and it is from DG set you are making off and then connecting to back to the DG set like. So, all synchronization with the DG set and all these are of course internal signal for control algorithm. Now, coming to typically power quality improvement in microgrid for electric vehicle charging station. For charging station, the concept is here we have here the solar PV generation, we have a vehicle charging here, and we of course putting this extra power to the grid, or we can take power from the grid through these voltage source converter. So, it is a multi objective reconfiguration 3-phase off board charger for. So, salient features is for household load, the charger acts as a standalone inverter, and for utility the charger acts as an active power filter, and voltage synchronization strategy for achieving the seamless mode transition between the grid connected and standalone mode, and reduction in the DG set rating operating in such a way that it generates 33% more power than its capacity, suppressing the rated current of the winding of the DG set. And this is the complete, let us say you can say control strategy logics for operation of this complete charging system, and the control algorithm for different modes of operation. And this is typically the standalone mode, that you have a 3-phase reference voltage and you have a frequency for synchronization, and you have a typically the algorithm for the extraction of the fundamental of load current. So, that you can have a amplitude of the grid current and the reactive current, how much you want to feed, and amplitude of the voltage, and the typically from line voltage the phase voltage calculation, and the reference current for calculation for active component, reactive component, and these are the template for which are used on those algorithms. And the system is implemented in standalone mode. So, you can see the TAD of the typically of the voltage quite low, in spite you are feeding non-linear load. But the grid current remains sinusoidal when it is connected to the grid. So, grid is not affected even by, so this voltage source converter providing the harmonic filtering here. And when you have a even an unbalanced voltage also, still we are able to have sinusoidal balance current in the grid line. And when the power of electric vehicle is changing, power virtually is typically accordingly changes into the grid, then vehicle to grid power. So, you are able to have power from the vehicle to grid, grid to vehicle, all modes. And when you have a typically feeding local non-linear load with the distorted voltage also, it work well the algorithm, and then you are able to provide the leading lagging reactive power also from these converters. And this is typically the synchronization. You are operating already with the earlier, when grid appears, then synchronization take place and you close the switch here and grid current start appearing like. This is typically another single phase charging station with the concept that you should be able to charge large number of like e-rickshaw or 2-wheelers. So, we have a very large storage battery, and we have a solar generation which we are charging into the battery. We have a grid if it is there, and we have a DG set if it is required. So, you have several EVs as well as you have a local load. So, it becomes like a good interesting charging station with the microgrid structure, providing the local supply also. And the features of power measurement are different sources, and regulation of voltage and frequency, and harmonic compensation of nonlinear load in standalone mode, and charging strategy design such that primarily take the power from solar array and storage battery. In absence of these sources, charging station take power from the grid, and when the grid is not there, then you take from DG set. And the reduction in DG set rating by, so that you can generate 33% more power by utilizing the DG set. This is the logic how you are going for power flow in this different operating mode, and then how you are going to in standalone mode for voltage generation load control, and typically the voltage control mode. And this is typically you can call it frequency control, the voltage control of this system, and the load extraction, and finally the getting signal for the voltage source converter, single phase voltage source converter. And these are the typical results where you can clearly see that you have a TAT of voltage current of 2.3% and 5% TAT of the voltage in spite of feeding the non-linear load and highly non-linear load in standalone mode, you are able to get even the quite good TAD of the voltage when you are feeding heavily non-linear load, and these are of course typically under the performance of non-linear load like also. Now, coming to the numerical problems, few numerical problem examples. A 3-phase AC microgrid consists of 30 kilowatt synchronous generator based on wind power energy conversion system, 24 kilowatt solar PV array indicated to 415 volt 50 Hz 3-phase AC grid, and solar PV array is connected at the DC link terminal of the back-to-back connected power converter used for controlling the synchronous generator. A linear load of 15 kilowatt is connected at the PCC terminal of the microgrid, and if renewable sources are operating at their rated condition, then calculate the RMS current injected into the grid assuming negligible losses. Power is injected into the grid at unity power factor, and this is the typical case you can see here. We have a wind power generation, we have a solar power generation here, and we have the grid exchanging this power to the grid. So, these are the typical data is given: wind power generation, solar power generation, then load, and we can find out how much the power going to the grid, 39 kilowatt, and then the grid current from power once we got from we get the grid current 54.257 ampere. Now, coming to example 7, a wind turbine coupled to doubly fed induction generator 4 pole 50 Hz. These are typically the data of blade radius gearbox and maximum power coefficient slip, maximum slip corresponding to your rated wind speed, and these are the PV array open circuit PV module current and MPPT voltage for PV module. So, back to back converters of microgrid connected to 415 volt 50 Hz 3-phase step up 2 to 1 transformer, and SP array connected to the DC link of through DC boost converter, and DC link voltage of the power converter are maintained at 360 volt with the renewable sources operated at 10 meter per second wind speed and rated solar PV rating. Calculate the required rotor speed, calculate the required duty ratio of the boost converter for maximum power from solar PV array and wind turbine. So, this is the pretty typical system of DFIG here. We have a solar PV generation here, and then we of course typically exchanging the power with the grid, and here is the non-linear load, typically linear non. So, this is about the wind power generation that we want to get the for maximum power tracking. What is the wind speed corresponding to in radian per second corresponding to 10 meter per second, and these are typically like what the voltage of PV are getting for a maximum voltage for PV for maximum power tracking, and then we can get the duty cycle corresponding to from the DC link voltage, which we are getting 360 volt DC link voltage and the PV voltage is 260 volt. So, this is the equation for boost converter. Now, coming to example 3, a 80 kilowatt synchronous reluctance generator based wind integrated system with the PV array with the peak power of 120 kilowatt, and the microgrid is connected to 84 kilowatt local load operating at 0.8 lagging power factor. So, net power is injected into the grid. If the renewable energy sources are operating at the rated condition, calculate the grid RMS current and the voltage current and kVA rating of the grid side voltage source converter. The reactive power compensation is provided by the microgrid, and no reactive power compensation provided microgrid. So, this is the typical system. We have solar, we have wind, and we have the grid with synchronization and islanding operation mode. So, we have here the wind power generation for 80 kilowatt, then solar generation 120 kilowatt, then load of 84 kilowatt. So, grid power comes by taking calculation is 116 kilowatt, and the reactive power of the load comes like a 63 from the typically 0.8 lagging power factor. We get the reactive power, and then we can find out the grid current at unity power factor from power and voltage 161, and we can find out kV rating of the grid side converter from Q and P. So, putting the all value here, we get the typically 209.688 kV, and the grid side voltage is already given 239, and the current rating we can find out the grid converter current rating from kVA divided by 3 into voltage, so 291.72, and then grid current corresponding to when we are without compensation. So, it comes typically from P and Q, it comes 183, and the grid side converter we can find out the rating from only for because it is providing active power not reactive power. So, and we can find out the grid voltage source converter current from this relation 278.242. Coming to fourth example, an AC microgrid with 120 kilowatt at rated wind speed of 12 meter per second square gauge induction generator based on wind turbine, and a 100 kilowatt at 1001 solar PV array feeding power to the 3 phases of 400 volt 50 Hz grid, and square gauge generator to the grid using back to back voltage source converter, and SP array is integrated to the common DC link of VSC through boost converter, a 480 volt battery energy storage system integrated with the microgrid through bidirectional DC converter to strengthen the wind and solar polarity. The microgrid control scheme designed to provide a smooth power of 150 kilowatt to 3 phase grid at all time. Calculate the battery current when the wind speed is 8.5 meter per second and the solar radiation 600 watt per meter. Also calculate the current injected into the grid. Also assume negligible losses, unity power factor and the grid side current varying the linear variation of solar PV power with irradiation. So, this is the system that we have wind power generation, we have solar generation, we have battery and we have grid integration here like. So, what we are getting here the solar generation typically the power corresponding to 600 watt per meter square. So, it comes 60 kilowatt and from wind maximum power for 8.5 meter per second we get this is 42 point. So, the net total power generated from wind and solar comes like 102.64 kilowatt and then we can find out the battery power from typically power generated and minus power of the grid minus the microgrid. So, it comes 47.36 and the battery is discharged. So, battery current we can find out typically from you can call it battery power divided by battery voltage. So, it comes 98.67 and current flowing to the grid we can find out from the grid power divided by root times 3 the line voltage, it comes to 16.5 ampere. Coming to example 5, a 12 kilowatt solar PV array is connected to the DC terminal of power converter used for the control of wind driven 25 kilowatt permanent synchronous generator. The microgrid is supplying the linear load of 8.5 kilowatt and 5.8 kVAr and remaining power is exchanged with the 415 volt 3 phase grid. The grid side voltage source converter ensure the grid always operate at UPF and the grid voltage source converter losses can be assumed 5% of the estimate A the load current and the grid current under the rated condition, B calculate the grid power factor and the phase angle shift between AC current with respect to the voltage. So, this is the system we have a wind generation from PMSG, we have a solar power generation and we are connecting this through grid converter to the grid line. So, coming to the solution SPRA and the wind are operating at rated condition. Thus, the net power of the wind is 25 kilowatt and SP is 12 kilowatt and the considering the loss is 5%. So, net VSC active power will be 95% of this because after 5% loss it comes 35.15 and the load active power is 8.5. So, the grid power from generation minus the load power it comes 26.65 kilowatt and since the grid voltage 415 line RMS. So, current flowing to the grid from you can call it from kVA divided by root 3 times of the voltage. So, it comes load current comes 14.32 and the grid current 415 volt and we know the grid power. So, we get the grid current 37 point. So, it is noteworthy that only the 3 phase active power is considered for calculating the grid line current. This is because the voltage source converter is ensuring unity power factor operation. Since the VSC control is ensure the grid always operating the grid line current always in phase with the corresponding voltage. However, in this case since the power is being fed back to the grid power factor is negative, thus the grid power factor is -1. Owing to UPF operation of the grid VSC supplied total load active power of 5.8 kVAr. Since the active power fed through the VSC is 35.15. So, phase shift of VSC phase current with respect to the voltage will be 5 Q tan inverse Q upon P and this comes 9.37 degree. So, we like to summarize with this. So, this microgrid power quality improvement in the microgrid. So, basic power quality related challenges microgrid have been discussed. Control scheme and performance evaluation of power quality improvement grid connected solar PV array battery based energy system based microgrid have been presented and control scheme and performance evaluation of power quality improvement grid connected and wind generation conversion system and battery array have been discussed and the control scheme and performance evaluation of power quality improvement grid integrated solar PV, small hydro and battery energy storage system based microgrid are presented and control scheme performance evaluation of grid connected integrated solar PV wind energy conversion system DG set battery energy storage system microgrid have been discussed and control scheme and performance evaluation of improve with the for electric vehicle charging station have been presented and these are the some of the references and thank you.